What's up, everybody, and welcome to OpenStax Algebra and Trigonometry, Chapter 1, Section 3, Radicals and Rational Exponents. Let's do it. What does it mean when a radical does not have an index? Is the expression equal to the radicand? Explain. So when we're talking about the index of the radical, we're talking about the little number that goes up here. So when there is no index, we assume that it's a 2. As such, if I had a radical without an index and 16, for example, this expression would not simply equal 16. This expression will be asking to take the square root of 16, which really asks the question, what times itself equals 16? That is, of course, 4. The only way this expression would ever be equal to itself is if I took a radical with a 5 and the index were 1. This really never happens, so this is the one exception, but pretty much assume no index and it's a 2. Every number will have 2 square roots. What is the principal square root? So when we're talking about a square root, let's say square root of 25. So when they're talking about it will have 2 square roots, check it out. The first square root that we think of is 5, because 5 times 5 is 25. The other root that also exists is negative 5. That's because negative 5 times negative 5 is still 25. That's because a negative times a negative is a positive. When we talk about the principal square root, it is the positive version. For this problem, we're asked to take the square root of 256, meaning what number times itself equals 256. Now, lucky for us, 256 is a perfect square, and the square root of 256 is simply 16. Boom, done. With a problem like this, first we're going to simplify the inside following order of operation. So 9 plus 16 is, of course, 25. Then we have the square root of 4 times 25. So what is 4 times 25? That is 100. Last but not least, we're going to take the square root of 100. Again, it's a perfect square. What times itself equals 100? That is 10. Boom, done. Here, again, we're taking the square root of a perfect square. 196 is a perfect square. So what number times itself equals 196? It is 14. So the square root of 196 is 14. Done. Here we're taking the square root of a number that's not a perfect square, but it does have perfect squares within it. So I'm going to show you how to simplify this. So we're going to do a prime factorization tree. 98 is simply 2 times 49, and 49 is 7 times 7. So now I can rewrite this as the square root of 2 times 7 times 7. And when I'm looking to simplify, I'm looking for perfect squares, aka twins. Because again, a perfect square is simply a number times itself to get that number. Well, check this out. I got a pair of 7s. So I can take the square root of 7 times 7, again, which is 49, and that is just a single 7. So it's like those twins come out as a single number. So it comes out like that. So my final answer simplified is 7 times the square root of 2. Boom, done. In this case, I've got a radical of a fraction. Now, I can rewrite this as follows. I can rewrite this as square root of 81 over square root of 5. Now, once I do that, this is pretty cool because I can see that the square root of 81 is 9 because 9 times 9 is 81. And then I have a square root of 5 on the bottom. Now, this is pretty much simplified, but generally we don't want to have a radical in the denominator. To get rid of that radical, what I'm going to do is I'm going to multiply by the square root of 5 over the square root of 5. This is allowed because this is simply equal to 1, so we're not changing the value of the fraction. On top, we're going to get 9 rad 5. On the bottom, we're going to get just 5 because the square root times itself is just the number. The other way to think about it is square root of 5 times square root of 5 is square root of 25, which of course is 5. This is the final answer. Done. For this one, we're going to try to simplify both of these first. Now, 169 is actually a perfect square. So the square root of 169 is 13 because 13 times 13 is 169. Likewise, 144 is a perfect square. That is 12 times 12. And then we add these together. 13 plus 12 is 25. Boom, done. In this one, 162 is not a perfect square. So we're going to try and simplify it first and then remove the radical from the denominator. So 18 over, now for 162, we're going to make another prime factorization tree, and we've got 2 times 81 gives us 162. That's a prime number. And then 81 is 9 times 9. Now, I can keep going, but I can already see I got a pair of numbers. Technically, I should keep going to do the prime factorization tree correctly, 3, 3, 3, 3, but I don't need to because this is really nice. So check this out. I can now say it's 2 times 9 times 9. There's a pair of numbers. That comes out as a single 9. Now I've got 18 over 9 rad 2. Now I can simplify the 18 over 9 and divide both by 9. So I've got 2 and 1. So now I've got 2 over 1 times rad 2, which is just rad 2. Last but not least, I need to get that radical out of the denominator. So I'm going to multiply by rad 2 over rad 2. And on top, I get 2 rad 2. On the bottom, I get rad 2 times rad 2. So again, a radical times itself just becomes the number without the radical. The other way to think about it is square root of 2 times square root of 2 is square root of 4. And square root of 4 is, of course, 2. Last but not least, I can simplify by dividing top and bottom by 2. Boom, boom. And I'm left with square root of 2 over 1, or simply square root of 2. Boom, done. So in this one, we can't combine these because I often think of radicals like variables. When they're different, it's just like different variables. They're not like terms. But what I can do is simplify 24 and recognize that 24 is simply 4 times 6. And we can even stop here because 4 is a perfect square. Then I can rewrite everything like so, and then I can take the square root of 4, and that comes out. The 6 stays trapped inside, and that's 2. And that comes out here and multiplies the number in front, the 6. So now I got 14 rad 6 minus 12 rad 6. Now we've got the same radical. These are now like terms. So now I can simply subtract the coefficients. 14 minus 12 is 2 rad 6. Boom. Since 150 is not a perfect square, I'm going to break it up into prime factors. So first I have 2 and 75. 2 is prime. Then I have 3 and 25. Now again, I could go to 5 and 5 and complete the prime factorization, but I kind of don't need to. Instead, I'm going to stop at this point because I recognize that 25 is a perfect square. So check this out. I'm going to rewrite this as 2 times 3 times 25. Then I'm going to take the actual square root of 25, which is 5, and that comes out there. Now I'm left with 5, and since 2 and 3, there's no more perfect squares left, I can recombine them. And we've got 5 times rad 6, boom, done. When we have a radical times a radical, the cool thing is the insides can actually multiply against each other. So square root of 42 times square root of 30 equals square root of 42 times 30, like so. Now to simplify this, I could multiply these together and get a giant number. Or instead, what I can do is I can start to break these up into factors. So for example, I can take 42 and know that it's 7 times 6. I can also look at 30 and know that it's 6 times 5. Now look at that. Again, we have twins. We have a perfect square as in 6 times 6. So we take the square root of that, and that's just a single 6, which we bring out here. Since 7 and 5 are both primes, there's no more perfect squares within them. So I'm left with 6 times, and let's recombine 7 times 5, which is the square root of 35. Boom, done. Now we have the square root of 4 over 225, both of which are perfect squares. So what I'm going to do is I'm going to separate the radicals, which I'm allowed to do in these fractions, and write it as the square root of 4 over the square root of 225. And then I'm going to take the individual square roots. So what times itself is 4? That's 2. What times itself is 225? That's 15. There we go. Boom, done. Again, I'm going to split this up as the square root of 360 over the square root of 361. This is pretty nice because the denominator is actually a perfect square. 361 is 19 times 19. As such, we get 19 on the bottom, but the square root of 360, we're gonna have to break that up a little more. So again, I could do a prime factorization tree, but right off the bat, I'm noticing something cool. 360 is 10 times 36. The reason why I like that is because 36 is a perfect square. So I can take the square root of 36, which is of course 6, and now I'm left with 6 rad 10 over 19, done. In this case, all I want to do is get the radical out of the denominator, so I need to figure out how to do that. But since it's not there by itself, meaning it's not just 8 over square root of 17, it's 8 over 1 minus square root of 17. I can't just multiply by a single radical. Instead, I have to multiply by something called the conjugate. So the conjugate is the exact same thing. It's 1 and square root of 17. But since there's a minus here, I flip that to be a plus. And since I can't just multiply by 1 plus square root of 17 on the denominator, I have to multiply that by that on the numerator as well, because then I have something over itself, the same expression over the same expression. Since that equals 1, this is feasible because this will not actually change the value of this expression. Now I'm going to multiply and distribute, and I get 8 plus 8 square root of 17 on top. On the bottom, we're going to FOIL. I've got 1 times 1, which is 1. 1 times square root of 17, which is square root of 17. Negative square root of 17 times 1. Again, that minus sticks to it. So that gives us a negative rad 17. And last but not least, I got negative rad 17 times positive rad 17. Again, the radicals will cancel out when it's the same number under those radicals, and I'm left with negative 17. These two are opposites, therefore they just cancel out like that. And then I got 1 minus 17, which is negative 16. So I've got 8 plus 8 rad 17 over negative 16. Last but not least, I'm going to divide everything by negative 8. And I've got negative 1 minus rad 17 over 2. Or alternatively, I can write this by pulling that negative out of the entire numerator and just throwing it in front like so, leaving me with 1 plus rad 17 over 2. Both answers are acceptable. Done. In this one, we've got an actual index of 3, meaning we're taking the cube root of these numbers. So instead of looking for twins now, I'm looking for triplets. So first, let's break 128 up into whatever we can possible. So 128 would be 2 times 64. 64 is 8 times 8. 8 is simply 2 times 4. Likewise here as well. And 4 breaks up into 2 times 2. So what I'm left with for 128 is the cube root of 1, 2, 3, 4, 5, 6, 7 2's. So once again, since I'm taking a cube root, I'm looking for triplets. So I see 3 2's there. That comes out. I see another 3 2's, and that comes out. And as they come out, they multiply each other. So then I get 4 cube root of 2 plus 3 cube root of 2. Again, now since we have the same radicals, we can add the 4 and the 3, just like if we were adding 4x plus 3x. That gives us 7 cube root of 2 for the win. Done. So here we have 15 times the 4th root of 125 over the 4th root of 5. So the first thing I'm going to do is I'm going to combine these into one fraction. So this becomes 15 times the 4th root of 125 over 5. This is pretty cool because 5 actually goes into 125, so I can say it's now 15 times the 4th root of 25. Now you might think, well, there's nothing that is to the 4th power within 25, so you might say, okay, we're done. But in fact, you can go a step further, so check this out. I can rewrite this as 15 times the 4th root of 5 squared. Then I can actually simplify this radical, and the way I can do it is if there is a common factor between the power and the index, I can actually divide by that greatest common factor and simplify this. So since it's 4 and 2 and they're both divisible by 2, I can rewrite it as 15 to the second radical 5 to the first. So I've simplified this. And by the way, I don't even need to write the 2 because it's the square root, so that's implied. I don't need to put the 1. So the final simplified form is 15 square root of 5. Boom, done. For the following exercises, simplify each expression. So we're taking the square root of 400x to the 4th. So we'll look at these two and take the square root of each of them independently. So first, the square root of 400, that's 20. That comes out like that. And guess what? X to the 4th has a perfect square root as well. It is x squared because x squared times x squared is x to the 4th. So our final answer is 20x squared. Boom, done. Here we've got 49, which is a perfect square, and p, which is not. So I can take the square root of 49, which is 7, but p is going to stay trapped inside the square root prison. So our final answer is 7 square root of p. So in this case, we've got a rational exponent, and I'm going to explain how to convert this into radical form. So the numerator represents the power that m is being raised to. The denominator represents the index of the radical. So this is the same as the square root. And again, I don't need to put a 2 here because when there's nothing, it's implied that it's the square root. And then inside it's m to the 5th times square root of 289. Now I could merge these, but the thing is 289 is a perfect square. So I'm going to take the square root of that, which is 17. I'm going to place that out there. Then I'm going to look at m to the 5th and see if there's any perfect squares in that. So of course, m to the 5th is m to the 4th times m to the 1st, I'll just say m. And m to the 4th, anything with an even exponent is a perfect square. So the square root of m to the 4th is m squared, so that can come outside. So I'll write it in our final format with the coefficient first, 17m squared with a m trapped inside the square root. Boom, done. In this first expression, we can take out the b squared because b squared is a perfect square. So the square root of b squared is, of course, just b. So now we have 3b times the square root of a minus b times the square root of a. Since they're both the same radicals here, we can subtract these coefficients. So 3b minus 1b is simply 2b square root of a, done. So here, the first thing I can do is I can actually simplify the x cubed over the x, because it's basically 3 minus 1. That's what we do with division. We subtract the exponents, and that's 2. So I'm left with simply x squared on the top, and the x is gone on the bottom. Now I can go through and start taking the square root of all of these, because guess what? They're all perfect squares, so that's really nice. So the square root of 225 is 15. Square root of x squared is x, and the square root of 49 is 7. Boom, done. So again, I want to try and find the perfect squares within 50. I already know y to the 8th is a perfect square because it's y to an even exponent. So I'm going to rewrite 50 as 2 times 25. I like that because I know 25 is a perfect square, so I'm not going to try and break it down any further. And y to the 8th is cool. So guess what? 25, the square root of 25 is 5. And the square root of y to the 8th is y to the 4th, because y to the 4th times y to the 4th would give us y to the 8th. So I'll write our final answer as 5y to the 4th square root of 2. Boom, done. So first things first here, I'm going to simplify this fraction by dividing 32 and 14 by 2, and we get 16 over 7d. So I'm going to split this up as square root of 16 over square root of 7d, and we can always split it up like that. That is not a violation of any rule. So then I'm going to say the square root of 16 is 4, and on bottom we have square root of 7d. Once again, we need to get rid of the radical in the denominator, so since it's a nice square root, I'm going to multiply by itself. So I'm going to multiply top and bottom by square root of 7d. And again, this is allowed because a square root of 7d over square root of 7d, it's the same numerator as denominator, so that's like 1. You can always multiply by 1, doesn't change the value of this fraction here. These guys multiply, and when you multiply a radical times its exact self, it just becomes what's under the radical, which is 7d. And on top, we get 4 rad 7d for the win, done. In this case, this is a little interesting because we have a part rational, part irrational. So what we have to do is we have to multiply by the conjugate to get rid of the radical in the denominator. We can also simplify the numerator, which I'm going to save till the end. So the conjugate in this case would be the same as this, except you switch the minus with a plus. So it's times 1 plus rad 3x, and we have to do the same on the top as well. So first we multiply this one over like so, and we get rad 8 plus rad 8 times 3x, which is 24x, over, and then we got a FOIL. So 1 times 1, which is 1, 1 times rad 3x, which is rad 3x, then negative rad 3x times 1, which is minus rad 3x, and then negative rad 3x times positive rad 3x is just going to be 3x, but since it's a negative and a positive, it's going to be negative. Now, these radicals, you notice they conveniently cancel out, and that's what we wanted. And then on the bottom, we're left with 1 minus 3x. The top were pretty much good, but we can extract more from these radicals. So for example, we know that 8 is 2 times 4. 4 is a perfect square, so we can take the square root of 4, and that's just a 2 that comes out. And this 2 remains inside the radical. Likewise, with 24, that is the same as 4 times 6. 4 is a perfect square. The square root of 4 is 2, and that's 6, and the x stays trapped inside, so we got 2 times rad 6x. This is the final answer, done. First, I'm going to rewrite these rational exponents in radical form. So again, the denominator represents the radical index, the numerator represents the power. So this is the same as the square root of w cubed, and this is the same as the square root of w cubed as well. So now recognizing that w cubed is the same as w squared times w in both cases, I can take the square root of the w squared, which is of course a perfect square. The square root of w squared is w, and what's left inside is a w. Likewise, 32 is 2 times 16. That's pretty nice because I know that 16 is a perfect square. So the square root of 16 is 4, and that 2 remains inside. Over here, we're going to do the same thing. We're going to pull out a w and leave a w inside. And I recognize that 50 is also 2 times 25. Now remember, if you don't see these perfect squares right there, you can just do a prime factorization tree and look for the doubles. Look for the 5 and the 5, because it would be 2 times 5 times 5. Oh, I got a twin of 5s. That's a perfect square. Take that out. But here, I'm just going to stop because I know 25 is a perfect square. The square root of 25 is, of course, 5. And that 2 remains trapped inside. Now I'm going to simplify by multiplying these together. Remember, the outsides multiply each other and the insides multiply each other. So I have 4w times the square root of 2w minus 5w times the square root of 2w. Now, since they share the same radical, I'm just going to do 4w minus 5w, which is negative w square root of 2w. Boom, done. In this case, I'm actually going to simplify that 12 first, because I know that 12 is the same as 4 times 3. And 4 is a perfect square, so I can take the square root of 4 and rewrite the numerator as 2 square root of the 3 stays trapped inside, and that x is going to stay there with it. And on the denominator, we've got 2 plus 2 rad 3. Now, the main objective here is to get rid of this radical in the denominator. And again, since I have a rational plus this irrational portion, I have to multiply by the conjugate. The conjugate is the same as this, but it's a minus instead of a plus. Once we get to this point, we're going to simplify the numerator first by distributing, boom, and we get 4, because the outsides multiply each other, 4 rad 3x minus 2 times 2 is 4 rad 3x times 3, the insides multiply each other, that's 9x over, and now we got to FOIL that denominator. So 2 times 2 is 4. 2 times negative 2 root 3 is negative 4 root 3. 2 root 3 times 2 is positive 4 root 3. And 2 root 3 times negative 2 root 3 is negative 4 times 3, because the square root of 3 times square root of 3 is just 3. So, and the 2 make negative 4, because of that minus. So we get negative 4 times 3, which is negative 12. Once again, these middle terms cancel out, and that's the point of multiplying by the conjugate, so we have no radical. And then we get 4 minus 12, which is negative 8. Now, on the numerator, I can simplify this part because I have a perfect square in that 9. The square root of 9 is 3. So I can take a 3 out, and remember, it's going to multiply that 4. So 3 times 4 is 12 rad x. And over here, we cannot simplify that, so that's 4 rad 3x. Last but not least, if you recognize what all the coefficients, they're divisible by 4. So dividing them all by 4, I get square root of 3x minus 12 divided by 4 is 3 rad x over negative 8 divided by 4 is negative 2. And just for fun, if I want to get rid of that negative in the denominator, I can take that negative out and apply it to the entire numerator and flip it, just so we have a positive denominator. It doesn't really matter one way or the other, but just to show you, then the 2 becomes positive. This then becomes positive. We'll throw that in the front. And this becomes negative for the final answer. Done. So here we're just trying to extract as much as we can from the square root. So I'm going to rewrite this as 125 is the same as 5 times 25. That's nice because 25 is a perfect square. And n to the 10th, well, it's an even exponent, so it must be a perfect square. So the square root of 25 is 5. That comes outside. The other 5 is going to stay trapped inside. So the square root of 25 is, of course, 5. And the square root of n to the 10th, what is that? It's kind of like dividing this by 2, because n to the 5th times n to the 5th is n to the 10th. So that's a perfect square we can remove there. And then, of course, the 5 stays trapped inside. Boom, done. So in this case, I could simplify the m over m squared to just leave an m in the denominator. But I'm not going to do that, because then I would remove the ability to completely take everything out of the radical on the denominator. So I'm just going to leave it as is, and I'm going to separate it into a radical on top of a radical. And the nice thing about 361 is it's a perfect square. So the square root of 361 is 19. The square root of m squared is m, so it's completely gone. On top, we have the square root of 81. That's another perfect square, which is 9. And then the m stays trapped inside for the win. Done. So here, everything is a perfect square. That's super nice. So I'm just going to, again, separate it out. You don't even really need to do this, but I will just do this just for fun. So the square root of 144 is 12. The square root of 324 is 18. And the square root of d squared is simply d. Now I can simplify. 12 and 18 are both divisible by 6, so I'm going to divide them both by 6. 12 divided by 6 is 2, and 18 divided by 6 is 3. There's our final answer. Done. In this case, I could divide the 162 and the 16 by 2, but I'm not going to do that because 16 is a perfect fourth power. But I will do it with the x to the 6th and the x to the 4th because it's going to remove the x completely from the denominator. So remember, when I have x to the 6th over x to the 4th, I subtract the exponents, which gives me 6 minus 4, which is 2. And that 162 I'll leave as is for now. And this is all over the 4th root of 16. And by the way, if I would have simplified earlier, it won't change the outcome. I'm just trying to show you the path of least resistance. So the 4th root of 16 is simply 2, because 16 is 2 times 2 times 2 times 2. So now we have a 2 on the bottom. And then on top, I'm going to rewrite 162 as 2 times 81. And the x squared as simply x squared. So the reason why I got the 81 is, again, you need to know this, and you may not know these perfect fourths. To recognize that 81 is special, we can do a prime factorization tree like so. So 81 is 3 times 27. 27 is 3 times 9. And 9 is 3 times 3. So guess what? 81 is 3 times 3 times 3 times 3. So it is a perfect fourth power. So the 4th root of 81 is 3. Now we're almost done. That means I can take the 4th root of 81, which is of course 3. So now the final answer is 3 times the 4th root of 2x squared over 2 for the win. Done. Now we've got cube roots here and here. So I'm going to show you the perfect cube within 128 with the prime factorization tree. So 128 is 2 times 64. 64 is a perfect cube. I'm going to show you why. 64 can be broken down into 4 times 16. And 16 is, of course, 4 times 4. Guess what? I got a 4, a 4, and a 4. That means 64 is 4 cubed. There's your perfect cube. In negative 16, it's going to be a little bit easier because it's negative 2 times negative 2 times negative 2 gives me negative 8. So that's the perfect cube root I can have there, and then I can pull out a 2. First, I'm going to rewrite it. So I've got the cube root of 2 times 64z cubed, and of course, since this is to the 3rd power, it's a perfect cube, minus the cube root of 2 times negative 8 times z cubed. So now I'm going to extract the perfect cube there. The cube root of 64 is 4. I'm going to take the cube root of z cubed, which is just z. And then I've got the cubic root of 2 left inside, minus the cube root of negative 8, which is negative 2. And the cube root of z cubed, which is z. And inside I've got the cubic root of 2. This is awesome because now I got the same cubic root here and here, so I can combine these. Minus a negative becomes a plus. So 4z plus 2z is 6z, cubic root of 2, boom, done. A guy wire for a suspension bridge runs from the ground diagonally to the top of the closest pylon to make a triangle. We can use the Pythagorean theorem to find the length of the guy wire needed. The square of the distance between the wire and the ground on the pylon on the ground is 90,000 feet. The square of the height of the pylon is 160,000 feet. So the length of the guy wire can be found by evaluating the square root of 90,000 plus 160,000. What is the length of the guy wire? So what I'm going to do is, just like every other example, I'm going to simplify first by adding those values underneath the square root. So 90,000 plus 160,000 is 250,000. And this just so happens to be a perfect square because 250,000 is the same as 500 times 500. So since we have a pair of twins of 500 and 500, the square root of this is simply 500 for the win. Done. So first of all, I'm going to rewrite 2 to the 1/2 power as the square root of 2. Again, anything to the 1/2 power, that's just the square root of that number. Then I'm going to simplify what's on the numerator as much as possible. So remember, 8 is simply 2 times 4. And that's nice because we can take the square root of 4, which is 2. So I have 2 times the remaining square root of 2 minus the square root of 16. 16 is a perfect square. Square root of 16 is 4 over, there's nothing we can do with this, it's 4 minus radical 2. Okay, now I see that I have a radical in the denominator. That's no good. I want to get rid of that. So what I'm going to do is I'm going to multiply by the conjugate of 4 minus rad 2. So I get 2 square root of 2 minus 4 over 4 minus square root of 2 times the same numbers here, 4 radical 2, but instead of the minus, a plus, and same on the numerator. Now I'm going to remember I got this minus rad 2, but I'm not going to write it until the next step. So on top, I'm going to FOIL, so I get 8 rad 2, right? The outside numbers interact. They do not interact with the inside number, plus 2 rad 2 times rad 2. Well, guess what? Rad 2 times rad 2 just becomes a 2, a liberated 2. So now we have 2 times simply 2, which is 4. Then we got negative 4 times 4, which is negative 16. And then I got negative 4 times rad 2, which is negative 4 rad 2. Over 4 times 4, which is 16. 4 times rad 2, which is 4 rad 2. Negative rad 2 times 4, which is minus 4 rad 2. And of course, negative rad 2 times rad 2. The rad 2's just turn into a 2, but the negative makes it minus 2, like so. Now on the denominator, these radicals, 4 rad 2 and negative 4 rad 2, cancel. So then we have 16 minus 2, which is 14 on the denominator. On the top, we can combine these guys. 8 rad 2 minus 4 rad 2 is simply 4 rad 2. And 4 minus 16 is negative 12. Then to further simplify, I can divide everything by 2, and I get 2 rad 2. When I say divide by 2, I mean the outside numbers, not the inside, the radical numbers. And then minus 6 over 7. And then we still got that minus square root of 2 over here. Last but not least, I'm going to try and consolidate this into a single expression. So I can get that nice common denominator by putting this over 1 and then multiplying the top and bottom by 7, because I'm not changing anything, right? Because 7 over 7 is 1. And since 7 times 1 is 7, I'm just going to remove that 1. So now I got 2 rad 2 minus 7 rad 2. Same radical, so I can combine that. So 2 minus 7, subtracting the coefficients, is negative 5 rad 2 minus 6 over 7. There's the answer. Boom, done. So here there's a lot of simplification that needs to happen. So the first thing I'm going to do is with these negative exponents, I'm going to move them down, since when they're negative, if I drop them to the denominator, they'll become positive. Since there's nothing left on the numerator, I'm going to place a 1 on top, and then I've got a to the 7th n squared times the square root of m squared c to the 4th. Now I'm not too worried about this negative 3, because what I'm going to do is I'm going to multiply across first and then start trying to extract things from the radicals. And you'll see that I'll just be able to add this exponent to this one because they're both under the radical, so they will interact. So on top, I have square root of mn cubed over a squared times a to the 7th. We add the exponents, a to the 9th. And then we still have an n squared times the square root of m squared. And then c to the negative 3 times c to the 4th. We add negative 3 plus 4, which is just c. Now I'm going to start to simplify. So n cubed is simply n squared times n. So I can take the square root of that n squared, which is n. So that comes out. And then the m and the n are left inside, over a to the 9th n squared. That m squared is a perfect square, so I'm going to extract that as an m with a square root of c left inside. So again, I don't mind the radical on the numerator. I just need to get rid of that rad c in the denominator. So I'm going to multiply by rad c, because when we're talking about square roots, I can just multiply by itself and it'll turn into just c. So last but not least, I have n times the square root of m, n, and c, because they're under the radical in multiplication. They interact and they combine, over a to the 9th n squared m, and then rad c times rad c is simply c. And because I have an n over n squared, those can interact. This cancels out with one of the n's. So our final form is rad mn c over a to the 9th n m c, done. Here on top, we've got a perfect square in 64. The square root of 64 is 8. So I'm going to bring that out. And of course, the y stays inside, plus 4 rad y. For the denominator, 128 is 2 times 64. So that's pretty nice. So I can take the square root of 64, which is 8. So I pull an 8 outside of that radical, and the 2 is left inside with the y. So now I need to get rid of this rad 2y on the denominator. So I'm going to multiply by rad 2y over rad 2y. And then so on top, we'll have to distribute. And again, the radicals will multiply each other. So I'll have 8x rad 2, and then y times y is y squared, plus 4 rad 2y squared, over Rad 2y times rad 2y is 2y. So then I'll have 2y times 8, which is 16y. Now I got perfect squares within these radicals. The square root of y squared is y. The square root of y squared is y. So now I'm going to rewrite this as 8xy times rad 2 plus 4y rad 2 over 16y. So even though they have the same radicals, they have different variables in these numerators. So I can't combine those, but I can simplify by dividing every coefficient by 4 and every expression by y, because they all have a 4 and a y in them. So I can divide this one and I would get simply 2x rad 2. I can divide this one by 4y and I'd simply get rad 2. And on the bottom, 16y divided by 4y is simply 4 for the win. Done. Here we've got a cube root, a fourth root, a square root, and a square root within another giant square root. So there's a lot of work to be done here. So first, 64 is a nice perfect cube because it's 4 times 4 times 4. So I can take the cube root of 64 as 4. 256 is something that is to the fourth power, which is 4 times 4 times 4 times 4. 4 times 4 is 16, times 4 is 64, times 4 is 256. So the fourth root of 256 is 4. Over the square root of 64, that's a perfect square. It's 8 times 8. So square root of 64 is 8. And 256 is a perfect square as well. The square root of 256 is 16. All of this is still under a square root. So 4 plus 4 is 8. 8 plus 16 is 24. Now I'm going to simplify this fraction to become 1/3, right? Divide top and bottom by 8, and I get square root of 1/3. Now I'm going to separate it out and make it square root of 1 over square root of 3. Well, guess what? The square root of 1 is just 1. And the square root of 3 is a problem. I don't want a square root in the radical, so I'm going to multiply by rad 3 over rad 3. Now, this will just become 3 because a radical times itself just becomes the number underneath the radical. And 1 times square root of 3 is square root of 3 for the win. Done. I hope you enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.